So one of the interesting things about optimization models, which make them more flexible and powerful, is you can often model the same problem in multiple ways, with multiple ways being correct. Now, of course, that sometimes will make things more difficult as well. So here we're modeling the same problem, and rather than saying we've got demands of 150, 450, we're actually just modeling in terms of the cumulative demand. So by the end of autumn, we need to have produced 150, by winter 550, and by spring 600. I mean, we could have actually had a row for demand and then created cumulative demand, but for this, let's just assume we're working with cumulative demand. We don't have, one of the things about this formulation is we don't have an explicit inventory variable. We just have three different production variables: how many produce in autumn, winter, and spring. Because, if we have production in autumn of, say, 300, we know that the inventory is going to be 150 without having it as an explicit inventory variable. Here, the inventory variables were basically used to help create the balance constraints in the first model, but we're going to do it slightly differently this time. So if we're going to match against the cumulative production, then obviously we're going to have to create a cumulative production constraint. So let's, cumulative production of August is going to be B12. Cumulative production in winter is going to be the previous production plus the production in winter. And cumulative production in the spring, we could have just done a Control R, but this works just as well. So say, for example, we had 50, 50, 50. Okay, you get that. The cumulative's gone up by 50 each time. Now, so the model that we have is basically, again, we have these production terms. We get charged a certain amount production, but rather than having an actual inventory variable, we calculate the inventory. We have the inventory cost of 1.2 and whatever's left over. Basically, the cumulative production minus the cumulative demand. So here, the cumulative production minus cumulative demand is how much we produce in the autumn minus 150. And by the time we get to the next period, it's production in the autumn plus production in the winter minus the 550 demand so far. And then we add production in the spring minus 600 demand. But in order to actually model this and multiply it by our whole inventory cost in the objective equation, we need to actually be able to calculate, for example, PA minus 150, PA plus PW minus 550. So basically, we have a variable here, not a decision variable, which is basically excess production. And that's just going to be the cumulative production minus the cumulative demand. And you can see, to start off with, we're not really in a feasible region here, because our constraints to manage this is that the production is greater than the demand at each period. So this should never be, if we run the optimization, this should be never negative. And I just mentioned the objective function. So this time we're actually going to need two sum products because we're not all in the same matrix. So this would just be the amount we produce times by the production cost. And then it's going to be our calculation of inventory. Kind of what I've called the excess minus the inventory holding cost. And at the moment, that just kind of is nonsensical, because obviously, given the constraints, we can't have an excess. So let's try and put this model into Solver. As it's the same model as before, I'm not going to bother with the answer analysis and the sensitivity analysis, but I'll just show you how to create it. So we want to minimize this by changing these three cells. subject to the constraints that the cumulative production is always greater or equal to the cumulative demand. And then we're going to make it a linear program. And this should actually give us the same result as last time. There we go, exactly the same result. That we've actually got the same, even though we have a different objective function, we have these two linear programs are mathematically equivalent, which we're not going to calculate mathematical equivalence of optimization problems in this class. That's a whole level of math, matrix algebra, that we don't want to get involved with. But you can see here that we calculate these excess is basically the inventory from the previous model. You see it's exactly the same values, but this time we calculate it, we don't model it explicit. So which model should I use? Well, this actually has less decision variables, so it's more elegant in a way. But quite often, you know, if you have a large linear program, you would actually see which one runs quicker because they're exactly the same. So you try and work out which one was the most efficient. Sometimes adding these extra explicit balancing constraints can make it easier to solve the simplex algorithm. But for the purpose of this class, I'm just saying that both of these are actually equivalent.